Hello everyone. In tonight's lesson, I'm going to start by going over a couple more problems from section 7.3 that are tied directly into WebAssign. And I'm just going to do part one. I'm going to split section 7.4 into two separate videos. So this will just be the first part. So I want to take a look at this example. We want to evaluate this integral. Now this is done a little bit differently than most examples in section 7.3, but we're still going to need some trig identities to help us out here. So I want to first rewrite this as the integral of 9x times the square root of 1 minus x squared squared dx. So now I'm going to let u equal x squared. That means du is going to equal 2x dx. Now if you notice, we see the x dx here, so that means I'm going to have to put the du over 2, and that's going to replace the x dx. So now I could put the 9/2 on the outside, so it's 9/2 times the integral of the square root of 1 minus u squared, and then just du, because I already put the 1/2 out in front. Now I'm going to replace this with a trig identity, or to turn it into a trig identity. So I'm going to let u now equal sine x. Actually, let's do sine theta, because I already have an x at the very top. I don't want to use that again. Now du is going to equal cosine theta d theta. So now when I go to replace this, I'm going to have 9/2 times the integral of 1 minus sine squared u times cosine, actually I did that again, theta, sine squared theta times cosine theta d theta. Now, why did I do this? Well, because right now I could rewrite this. I could rewrite it using the trig identity. Remember, 1 minus sine squared, if we go back to a Pythagorean identity, that's just cosine squared theta. So now I get 9/2 times the integral of the square root of cosine squared theta times cosine theta d theta. Now I can take the square root of cosine squared theta, which is just cosine theta times cosine theta d theta. Now I can write this as cosine squared theta, so it's 9/2 times the integral of cosine squared theta d theta. Now I have a couple choices here. The easiest one to try to use is the Pythagorean identity, but if I go back to 1 minus sine squared theta, that's not going to help us out too much. There's another identity, the half angle formulas here, where cosine squared theta is going to equal 1/2 times the quantity 1 plus cosine 2 theta. So I'm going to use that identity. So now this becomes 9/2 times the integral of 1/2 times the quantity 1 plus cosine of 2 theta d theta. Now I could pull that 1/2 out in front, so I'm going to get 9/4 times the integral of 1 plus cosine 2 theta. And now I could take the integral of each of those terms. So I'm going to have 9/4 times the antiderivative of 1 is just going to be theta, plus the antiderivative of cosine 2 theta is going to be sine of 2 theta. But if I took this derivative, I'd have an extra factor of 2, so all I have to do is put the 1/2 out in front, and then we have plus c. Well, I want to get things back in terms of x, so I have to kind of go back 2 steps. First, we used u. So over here to the side, I am going to make my right triangle now. So remember we said u was equal to sine theta, or sine theta is equal to u. So now if I make my right triangle, here's where I'm going to put theta. So this is really u, or u over 1, so that's opposite over hypotenuse. So here's the opposite side, u. My hypotenuse is 1. That makes the other leg the square root of 1 minus u squared. And if we go back a few steps, I have this right here, 1 minus u squared underneath the radical, which is nice. But there's a couple other things I need to do. I need to get theta by itself. So if sine theta is equal to u, then theta is equal to the inverse sine of u. So right now I could rewrite that 9/4 times the inverse sine of u, or arc sine of u, plus 1/2. Now there's another trig identity here I'm going to use for this, and that is that sine of 2 theta is equal to 2 sine theta cosine theta. So that's how I'm going to rewrite this. 2 sine theta cosine theta. And the reason I did this is because I can figure out, I already have sine theta, I could figure out what cosine theta is and just substitute those in. So cosine is adjacent over hypotenuse, and then that's just the square root of 1 minus u squared over 1. So now this becomes 9/4 times the inverse sine of u. 1/2 times 2 is just 1. So now I have sine theta, which is just u, times cosine theta, which is the square root of 1 minus u squared, plus c. But now I have to go back in terms of x. So if I go all the way up to the top, u is equal to x squared. So anywhere I see a u, I need to replace it with an x squared. So now we get 9/4 times the quantity of the inverse sine of x squared plus x squared times the square root of 1 minus x squared squared is x to the 4th, and then plus c. Now you could distribute that 9/4, or you could leave it like this. Again, you could have inverse sine of x squared. You can have arc sine of x squared, but this would be our final answer. Let's take a look at another one. This is a definite integral. We'll go the definite integral from 0 to 3 of dt over the square root of 9 plus t squared. So now if you take a look at our notes, we really have like an a squared plus x squared, or in this case a squared plus t squared. So we want to let t equal a times tangent theta. So a is 3, and then tangent theta. And then this allows us to say that dt is 3 times secant square theta d theta. Now keep in mind, when I'm going to switch to thetas, but I'm still going to use the 0 and 3, so I'm just going to remind you that it's t. We don't want to substitute them in for theta. We have to get everything back in terms of t. So now this will become the integral from t equals 0 to t equals 3 of 1 over square root of 9 plus the quantity 3 tangent theta squared, and then we'll have times 3 secant square theta d theta, because that's what we're replacing our dt with. So again, it's t equals 0 to t equals 3. The integral of 1 over, we'll have 9 plus 9 tangent square theta times this again. Now when we get to this point, we want to factor out a 9. Now I'm showing every step. If you are comfortable with skipping some steps, that's fine. Just be very careful. So I'm going to factor out a 9, and then I'm left with 1 plus tangent square theta. And we can replace 1 plus tangent square theta with what? Secant square theta. And by doing this, now we can go ahead and actually take that square root. So we'll simplify this next. So this just becomes 1 over 3 secant theta. And now we can see that we can divide some things here. So clearly the 3's are going to be gone, and then secant square theta divided by secant theta is just secant theta. Now, a couple sections ago, I think it was section 7.2, I did some examples where we just took the integral of secant x dx and then the integral of tangent x dx. So we could use that now. If you recall, the integral of secant theta d theta is going to become the natural log of the absolute value of secant theta plus tangent theta. But we need to evaluate this again from t equals 0 to t equals 3. So I need to replace the thetas in with something in terms of t. So this is where I go over to the side and make my right triangle. So if t is equal to 3 tangent theta, then tangent theta is equal to t over 3. And I make my right triangle. So tangent is opposite over adjacent. So the opposite side is t. Adjacent is 3. That means the hypotenuse is the sum of their squares. So there's the 9 plus t squared. And then I need to write something for secant theta. So secant theta, remember secant is the reciprocal of cosine. Cosine is adjacent over hypotenuse. So secant is hypotenuse, which is this radical, over adjacent, which is 3. So now this becomes the natural log of the absolute value of the square root of 9 plus t squared all over 3 plus tangent theta, again, is t over 3. Now I no longer need to write t equals because everything is in terms of t now. So now I just evaluate. So I'm going to have the natural log. Now what's nice is once I substitute these values in, everything's going to be positive, so I could technically lose the absolute value symbols. So this is going to be, when t is 3, this is 9 plus 9, so it's the square root of 18 over 3. And then 3 over 3 is 1. Then minus the natural log of 0, if a 0 is going in for t, that's the square root of 9, which is 3 over 3, which is 1. And then 0 over 3 is just 0. So I'm going to simplify this. So if I looked at radical 18, if you recall, I could write this as square root of 9 times square root of 2. So this becomes 3 radical 2. So I get 3 radical 2 over 3, which is just radical 2. So I just want to show you where I'm getting that from. So here I get the natural log. Again, this is 3 radical 2 over 3, so it's just radical 2 plus 1. And this just becomes a natural log of 1, which is 0, so this is our final answer. So quite a few steps, but very necessary to show all of this. All right, so let's go ahead and start the first part of section 7.4, which is called partial fractions. All right, so what we're really doing, this is another technique of integration when none of the other methods are working. So I'm just going to start off with an example, just kind of jump right into it, and then I'll go over the pieces of, like if our problems look like this, what do we do? So the different conditions. So let's first start with this integral of 1 minus x over the quantity of x squared plus 3x plus 2. Use substitution, integration by parts may not be very helpful here. So what we're going to do is we're actually going to factor the dx there. We're going to factor our denominator. Remember, it's always easier to take the antiderivative or evaluate an integral of terms rather than a single expression like this, because we don't have the quotient rule for integrals. We have it for derivatives, just not for integrals. So this denominator will factor into the quantity of x plus 2 times the quantity x plus 1. Now what we do is we decompose this fraction. So I'm just going to take the fraction out of the integral for right now. So if I have 1 minus x over this quantity here, this product, what I could do is separate it in what we call decompose into separate fractions, what we call partial fractions. So I know I could get this common denominator if my first denominator happens to be x plus 2, and then I add it to a second denominator, or second fraction whose denominator is x plus 1. Well, I have no idea what the numerators are going to be. So I could just call the first numerator a and the second one b. So I know if I were to get common denominators here, I would have to multiply a by the x plus 1, because it already had the x plus 2. Then I'd have to multiply b by the x plus 2, because it already had the x plus 1 as its denominator. And I'm just looking at the numerators here, so both of these together would have to equal the 1 minus x, the numerator that's over here. Well, now I just pick certain x values. So I'm going to first let x equal a negative 2. I chose that over here because if x is negative 2, my b term goes away. So this causes my coefficient for a to be a negative 1, so I'll get a negative a. Negative 2 plus 1 is negative 1 times a. Negative 2 plus 2 is 0. 0 times b is gone. And over here, I'm going to get a negative 2 minus x, and that will give us, 1 minus a negative 2. I read that completely backwards. 1 minus a negative 2 will become a positive 3. Then that means a would equal a negative 3. And I'll do just the opposite here. I'm going to let x equal a negative 1. That means my a term goes away. Now negative 1 plus 2 is 1, so I get a 1b. Now this is 1 minus a negative 1, so that's going to equal 2. So now I have my numerators. So now we would say that the integral of 1 minus x over this denominator can now be separated into a over x plus 2, so negative 3 over x plus 2, plus b over x plus 1, so 2 over x plus 1 dx. Now it's a lot easier to take the antiderivative of each term. This is just going to become negative 3 times the natural log of the absolute value of x plus 2. And just check, if we were to take this derivative, we would get negative 3 over x plus 2. And then plus 2 times the natural log of the absolute value of x plus 1 plus c. So this technique is called partial fractions. So let's take a look at the different ways that we can approach this decomposition. And we call it this is because normally we're given a couple fractions. We want to add or subtract them together to make one fraction. Well, now we're taking one fraction and we're separating them into individual fractions. So the first rule, what we're always trying to see for this decomposition to work like the last example I did, the degree of the numerator must be less than the degree of the denominator. And degree is the largest exponent to show up. So the degree of numerator must be less than the degree of the denominator. Well, what happens if it isn't? We got that covered. If not, remember back in Algebra 2 or maybe a college algebra class, you had to go through long division, polynomial division, which turned into synthetic division as a shortcut. This is where we use it. So we perform long division. So we'll go through an example of this. So let's say we want to evaluate the integral of x squared minus 4x plus 3 over x minus 2 dx. Normally what we would try to do is perhaps factor the numerator, maybe cross out some common factors, but that's not going to help us here. So what we do is we actually divide this out. So let's review what polynomial long division looks like. The numerator goes inside the division box, and the denominator goes outside. So we're going to get our quotient here. So notice we have every term here. We have an x squared, we have an x to the first, and then we have our constant. That's good. If we were missing any terms in between, we'd have to fill them in with a 0. So now x squared, or x goes into x squared, just x times. So if I multiplied x times x, I'd get x squared. Well, here's my x term, so I'm going to put it over that. Then I go back and I multiply. X times x is x squared. X times a negative 2 is a minus 2x. Then I subtract. X squared minus x squared is gone. Be careful here. Negative 4x minus a negative 2x, that becomes a negative 4x plus 2x. I get a negative 2x. Then I bring down my plus 3. So now x times what is negative 2x? A minus 2. Notice how my constant is going over the constant here. Negative 2 times x is negative 2x. Then I get a plus 4. I'm still going to subtract here. So negative 2x becomes a plus 2x. That's gone. Then I get a 3 minus 4. So then I get a negative 1. That's my remainder, but this is how we write it. We're going to say minus 1 over this fraction here, kind of like how we do a mixed number. So now I have this fraction separated into terms. So now the integral of x squared minus 4x plus 3 over x minus 2 dx becomes the integral of x minus 2 minus 1 over x minus 2 dx. Now this version of it is so much easier to take, evaluate the integral for, take the antiderivatives. Antiderivative of x is just going to be x squared over 2 minus 2x minus, this is just the natural log of the absolute value of x minus 2 plus c. How could we check? Just simply take the derivative of this. And we would, if we got all of these into have a common denominator, we would end up with that fraction at the very top. All right, so again, If our numerator has a degree that is larger than our denominator, this is the approach we take. All right, rule number 2, we could factor the denominator as much as possible. So that's if our numerator is 1 degree less than our denominator. We want to factor the denominator as much as possible. Now, there's going to be different cases here. I'm just going to look at the first 2 cases to finish up this section, and then in the next part of the video, we will continue on. So all denominators factor into products of irreducible linear or possibly quadratic factors. That means we just keep factoring, and they're all going to factor into either linear, like binomials, or quadratic factors. We say irreducible, it just means the same thing as prime factors. So again, as I mentioned, there are several cases. All right, the first case is that the denominator is a product of simple linear factors, none of which are repeated. So let's take a look at an example here. Now for this one, I'm just going to focus on decomposing the fractions. In our next part, the next case, we'll do that, but then we'll also tie it into an integral so you could see the full scope of the problem. So let's say our fraction that we're looking at to decompose is 6 over the quantity x minus 1 times the quantity x plus 3. So we want to decompose this. So I'm going to write this as a over x minus 1 plus b over x plus 3, much like our very first fraction. So this means if I wanted to get this common denominator here, I'd have to multiply a by the quantity x plus 3 and b by the quantity x minus 1, and all of that combined would have to equal this numerator of 6. So now I just pick some values for x. Let's start, I always like to get rid of the b first, so let's let x equal 1. Then I'm going to get 1 plus 3, I'm going to get a 4a. 1 minus 1, my b is going to go away because that's going to be 0 times b. That's going to equal 6. So a is going to equal 6/4. We could leave it like this. Then let's let x equal negative 3. That way my a term is going to go away, and I'm going to get negative 4b is equal to 6. So b is going to equal negative 6/4. So now I can go back to my fraction and say, well, 6 over the product of these two binomials can be separated into 6/4 over x minus 1 plus, actually, instead of plus a negative, we could just say minus 6/4 over x plus 3. Then we can integrate this term by term. Now there's other ways you can simplify this as well. All right, let's look at our second case. Here the denominator is a product of linear factors, some of which are repeated. let's go ahead and decompose x squared minus x plus 3 over x squared times x plus 1. So in this case, we have to build up. What I mean by that is when we're looking at this x squared, we first have to do a over x, then plus b over x squared. Then we have a third fraction of c over x plus 1. Now, if we had an x plus 1 squared, I would still need the c over x plus 1 and then a d over the quantity x plus 1 squared. And in the next part of the video, I will go over examples like that. All right, so now we would show that a, to get this common denominator, a already has a factor of x, so it needs another x, and then it needs the x plus 1. B already had the x squared in its denominator, so it just needs the x plus 1. And then C already had the x plus 1, so it just needs the x squared. Now all three parts of that need to equal this numerator, x squared minus x plus 3. All right, so let's start with x equals 0. I want to get rid of that c term first. So if x is equal to 0, that means my a term is also gone because of this x right here. And I'm just going to get 0 plus 1 times b, which is just b. Over here, I'll get 0 minus 0, so I'll just get a 3. So b is equal to 3. Next, let's try x is equal to a negative 1. So that's going to help here. If x is equal to negative 1, a is gone, b is gone, so I'm just going to get a positive 1c. When I square a negative 1, that's positive c. And then over here, I'm going to get a positive 1 minus a negative 1. So I'm going to get 1 plus 3. So c is equal to 5. Now I don't have any other choices that something is going to cause a, b, or c to go away, and that's fine. I could just pick another nice, easy value to work with. Let's let x equal positive 1. Because I already know what b and c are, this can help me find a. So this leads me to say this is going to be 1 plus 1 is 2 times 1 times a. So I'm going to get a 2a. 1 plus 1 times b here is going to be a 2b. And then plus c. This will give me a 1 minus a 1. And then it's just going to give me a 3. So I already know b is 3. So I have 2a. 2 times 3 will give me 6. C is 5. That's 11. So if I subtract that, 3 minus 11 is negative 8. So a is negative 4. So now I can rewrite my fraction. And I'm actually going to turn it into the integral now. So if I were to ask you to evaluate the integral of x squared minus x plus 3 over x squared times a quantity x plus 1 dx, I can now rewrite this as the integral of a over x. A was negative 4, so we get negative 4 over x, plus b over x squared. B was 3 over x squared. And then plus c over x plus 1, so 5 over x plus 1 dx. And now I could just take the antiderivative of each term. So this is just going to become, of the first term, negative 4 times the natural log of the absolute value of x. We could think of this as 3 times x to the negative second. So I don't use the natural log here. I just use the power rule for antiderivatives. So this will become plus 3 times x to the negative first over negative 1, because we're adding 1. And then this will become 5 times the natural log of the absolute value of x plus 1 plus c. So we could leave it like that, or you could turn this into, this will just become a negative 3 over x if you wanted to write it this way, but this is perfectly fine. All right, so let's take a look at 2 more examples of what we already talked about. And you can feel free to pause the video to give these a try on your own, just based off of the notes so far. So let's do the integral to evaluate this of x to the 4th over x minus 1. So remember, we really want to make sure that our degree of our numerator is 1 less than the degree of our denominator. In this case, it isn't. So that was that very first rule for decomposition here that we want to use long division. Now I'll get you set up with this, and then again, if you want to pause the video to try some more on your own, you can. X to the 4th is going to go in the division box, but I need more there because x minus 1 goes on the outside. I don't have an x cubed, x squared, x, or constant term, so I have to fill those in with 0. So 0x cubed plus 0x squared plus 0x plus 0. So pause the video if you wish to try this on your own. If not, just continue to follow. So x times what is x to the fourth? X cubed. So I'm going to put that over my x cubed term. Multiply both by x cubed. So I'm going to get x to the fourth minus x cubed. Then we subtract. So my x to the fourths are gone. Then I get 0 minus a negative x cubed. So I'm going to get a positive x cubed. Then I bring down the 0x squared. So x times what is x cubed and x squared. So that goes here. Multiply x squared times x is x cubed. Then we get a minus x squared. And we subtract. X cubed minus x cubed is gone. 0 minus a negative x squared becomes positive x squared. Then I bring down the 0x. X times what is x squared? X. So x times x is x squared. Then I get a minus x. Subtract. X squared minus x squared is gone. 0 minus a negative x is x. Bring down the other 0. X times what is x? 1. Multiply, so I'll get an x minus 1. Subtract, x's are gone, and then I get 0 minus a negative 1, it's 1. So I write my remainder as plus 1 over x minus 1. So now I can say the integral of x to the fourth over x minus 1 dx becomes the integral of x cubed plus x squared. So I'm just rewriting. So this means if I were to get all of these with the common denominator of x minus 1, it would just turn into x to the fourth once I combined everything. So then I get plus x plus 1 over x minus 1 dx. And now I could just take the antiderivative of each term. So this will become x to the fourth over 4 plus x cubed over 3 plus x squared over 2 plus x plus the natural log of the quantity x minus 1 plus c. We need that absolute value around the x minus 1 though. Okay, let's try our second example. This will wrap up the first section here. All right, let's go ahead and integrate the evaluate the integral 26x plus 4 over, now this is already factored for us, 5x plus 1 times the quantity x minus 1 dx. Now, the numerator only has a degree of 1, but if I were to actually multiply these two binomials together, I would first get a 5x squared. So the degree of our denominator is 2, which is 1 larger than our numerator. So I want to decompose this fraction. Again, if you wish to try this on your own, go ahead and hit pause and try this. But what this is going to equal is a over 5x plus 1 plus b over x minus 1. Now this becomes a times x minus 1 plus b times the quantity 5x plus 1, and that's going to equal 26x plus 4. So I'm going to go ahead and let x equal 1 here. This will allow me to solve for b first. So again, this is 1 minus 1 times a, which is just gone. Next, I'm going to get 5 times 1, so 6b. And when x is 1, that's 26 plus 4 equals 30, so b equals 5. Now, I don't want to use a fraction here, so we could just pick a nice value. We could say maybe let x equal 0. Then we're going to get a negative a, and then we'll get a plus b. And then over here, this will just leave us with a 4. Now, b is already 5, so I have negative a plus 5 equals 4. This means negative a is going to equal a negative 1. And a equals 1. So I found the values for a and b. So now I could say that the integral of 26x plus 4 over this denominator All right, so again, this integral now can be rewritten as the integral of a over 5x plus 1. So that's 1 over 5x plus 1 plus b, which is 5 over x minus 1 dx. And we just take the antiderivative here. So the first is going to become the natural log of the absolute value of 5x plus 1. But we have to be careful here, because if we did take this derivative, we would get 1 over 5x plus 1, but then we'd have the derivative of the inside stuff, which would be times 5. So I have to put a 1/5 here. And then over here just becomes 5 times the natural log of the absolute value of x minus 1, and then we get our plus c. All right, so please let me know after you're done watching this if you have any questions. Like I said, the second part, we will definitely take a look at other scenarios, other situations.